Hello everybody. If you've been watching my channel over the last few months, you might have found yourself thinking it's only a matter of time before old iForce 2D tries to build himself a pick and place machine. Well, here we go. We've finally got started on it. I've been investigating this for quite a while, and I've even made a start on some of the components for it, like the camera control and stuff like that. But I hadn't made any actual machine, but obviously I have started doing that now, and I have designed it all in Onshape as we're looking at here. It's about 60 centimeters square, this aluminium plate will be at least, so not too big. I'd like to have it something that I could kind of maybe pick up and carry around. That would be nice. I have not made the aluminium plate yet. I've just made an MDF sort of a mock-up test piece just to see if everything's going to work. But I have made just about everything else we see here, at least the main motion components, as I would call it, the sliding around of all these bits. And I haven't made this bit down here yet, but I think I'll just jump straight into it without further ado, because I'll be waffling about stuff as we go forward anyway. But yep, this is the design, and hopefully this is how it's all going to turn out. When I cut these with my miter saw, they're not terrible, but they're just not, you're probably not going to be able to see it there, but they're not square. I wish I had a saw like they have at the place where I get this aluminium. I just measured this one. This is their end that they cut. It's incredibly square. But my miter saw doesn't do that, unfortunately, so I'm cutting them a little bit long, and then I'm putting them in this little jig, and I'm just chopping the ends off. And this is one that I just did, but like I say, you probably can't tell the difference. But it's now perfectly 5 centimeters or 50 millimeters long, and it's perfectly square on each end. And very soon all these other ones are going to be like that as well. And obviously I've made this jig way longer than that one, because I'm going to be putting this and a couple of other even longer ones in here as well, so it goes all the way out to there. Well, that worked beautifully. We've got some nice 3mm holes there, and then some 2.5mm holes here, which I'm going to have to tap. This is where the linear rail is going to go. This is the gantry beam that I'm holding. And then we've got some more symmetrical kind of holes down there. And then I'm going to have to use the drill press to drill through this, and then hole out onto the other side, so that they can, so they're gonna like sit on there.
Oh my goodness.
I had my screwdriver and I was just like 1 second too late to push that bit out of the way. So after a whole bunch of machining and tapping, these once ordinary boring aluminium extrusions have been transformed into some rather nice fancy little things. This is the gantry, and then these two pieces here are what goes below the gantry, and they are identical, which is kind of nice, perfectly matching up. And this is where the rails for the what is this, y-axis, I think most people would call that the y-axis, that's going to go on there. And then these holes here match up with the holes underneath. So I did 3 sides of machining, but because it's square you can use the same jig for everything. You just loosen it, slide it out, tip it over 90 degrees and slide it back in. So it's not as much of a pain in the ass as making the wings for the twin hopper was, with having to use pegs to get everything in the right place. This is way easier. Anyway, so this hole here is for the head of that bolt to go in. I can just get it to sit there like that. So it's going to go in there. Not that long, of course, but a shorter bolt will go in there and we'll be able to tighten it down from the top. I moved all this stuff over here next to my main computer because I'm going to be doing a lot of development and I want to be able to, test and check things quickly. I've been trying out the XY movement here and it's been working very, very well. I'm really happy with it. And the next thing to do is to figure out the Z movement, and the first thing I tried did not work. You can see here roughly what's going on, and I'm just about to dismantle this because it was kind of a fail, but I thought I'd show you. I'll show you what does not work. The motivation for doing this is that I did not want to have a motor on here to do the Z movement. I wanted to keep this moving part as light as possible so that it could accelerate quicker and it would only need a smaller motor on here, and that in turn would mean that the gantry could be lighter and the whole thing that moves that way would be lighter, and then that motor would be able to accelerate things quicker in the Y direction as well. The other thing about this is that you can have a stronger, faster motor, which is what I have up here, really big one, because once you've taken the weight off of the moving part and put it somewhere else, it doesn't matter how big and clunky it is. And you could also have, say, 3 motors if I wanted to have 2 or 3 nozzles. I'm not adding any more weight to this to add 3 more vertical movements on here. So that was the motivation for it. Unfortunately, it's not working out very well. And the way it was supposed to work is there's a Kevlar thread in there, which goes round those little rollers at the bottom, and on this side it's tied onto the side of this carriage that moves moves vertically. And in here we have it going into some PTFE tubes, and it's coming over the top of this rolly bit there, and there's an M8 bolt which I found if you just wrap the Kevlar thread around it you get a surprising amount of friction. So I was going to say it doesn't slip, but what I'm about to tell you next is I was having some problems. So I'm not 100% sure that it's not slipping, but I'm like 99% sure it's not slipping. And then there's a big NEMA 17 to turn that. And when I turn this here, it moves nice and smoothly and easily. Everything feels fine, and it moves okay down there. But we have a problem. There's some backlash. Probably about 1, maybe even 1.5 millimeters of backlash. Mostly when I go down and then come back up. So you're not going to be able to tell that from the video, but trust me, there's some backlash. So when I saw that, I thought, okay, that's probably the end of this idea. I don't really want to have to deal with that. The other problem is that even though I can turn it nice and smoothly here, and when I use the Linux CNC's jog feature, you know, you just press the keys on the keyboard to move it up and down, that also works nicely as well, apart from the backlash of course, but it just sort of moves smoothly and everything's great. But then when I try and run some G code where the acceleration is going to be a little bit higher, all of a sudden something slipping, and it makes a little bit of a sort of a creaking wood kind of a noise, and I just can't figure out what's slipping, and I just don't want to deal with it really, because the acceleration that I'm testing with is nothing even close to the acceleration that I want to get from it. Like I want this piece to be going up and down nice and fast as well. So for all those reasons, I'm just going to abandon this silly idea, and I've got my plan B over here. I'll put that together in a minute and show you what that's all about. It's a little bit more traditional approach. Okay, well that second revision of the vertical axis here works awesome. Way better than the first one. A little bit heavier, but I don't think it's really going to matter. So I think I'm just going to finish this video here. This is not the kind of thing you slap together very quickly, so it's going to have to be a multi-part series. But I just realized that I've glossed over all of this other stuff here and haven't really given much of an overview of what other components are being used here. I think you've seen here there's a NEMA 23, a NEMA 17, and NEMA 14 here, and then there's a NEMA 8. And the XYZ motors all have closed loop steppers. I'm using these pretty nice ones. Nice but not expensive, which is good. So there's a CL57 for the NEMA 23, and then there's a CL42 for the other two. That one has an optical encoder. And these ones, I wanted them to be smaller and lighter, so they're just using magnetic encoders. Seem to be fine though. Does make it a lot smaller and lighter. And then the NEMA 8 on here has no encoders, hoping that, you know, it doesn't really have much load on it. and the only load that it's really going to have is it has to twist this. I'm going to try using this silicone tube. It's nice and soft, and all it has to do really is twist it a little bit. I'll just get that out of the way. Just has to twist it like that, and I'm only using 200 milliamps at 12 volts, which is about 2.5 watts, and it seems to be functioning perfectly fine. It can go 200 degrees in each direction, which is all it's going to need to do, and it's been running for hours, and I can just barely feel a little bit of warmth. So that 200 milliamps is going to be fine, but I could go a little bit higher really if I needed to. These are running at 800 milliamps each, all at the moment, and they're all nice and cool. So could go a lot further with these stepper drivers, but don't think I need to. What else have you got here? So these bits, I guess you saw how those were made. The belt goes inside there, rather fancy design. Usually when I make a fancy design like that, something goes wrong, but this time it all worked out quite nicely. And again, here we have a fancy design where the belt is going inside like this. These little things here are my custom made limit switches. There's an optical photo transistor thingy there, and I actually had those made by JLC PCB, and they put the small components on, but then I bought the actual optical thingy separately off AliExpress because I didn't want 160 of them. The only problem with these is that when you buy them on JLC PCB, because they're so small, you need to panel them together to a minimum size, and then you need to order a minimum of 5 of that panel. So there's 32 on a panel, and so I got 160 of them, but I only wanted 6 really, so now I have 154 of them that I don't need. But that's all right, they didn't cost much. So I haven't got those hooked up yet. I have checked that they work and everything, but they're going to have a little piece of stout shimmage, aka aluminium can probably, stuck on here, and that's going to poke between there when it comes over this. Oh, I can't move it because it's powered up at the moment. Everything's powered up. Yeah, I was going to talk about this stuff, wasn't I? Got distracted. So what we're running this with is a Raspberry Pi 3 B+, and it's going through this SPI connection to my Weenie PRU, and we have some TMC 2209 stepper drivers on there. I'm actually only using this fourth one here for the A axis for the rotary, the nozzle. The other two over there are doing nothing. All of those step and direction outputs are coming into the closed loop stepper drivers there. I don't think I've mentioned this in the video yet, but I added the UART control support, and it's also controllable from Linux CNC. So I could potentially, if I needed to, change the current for this motor here on the fly using G-code. If for some reason I suddenly wanted it to do, it's rated to go up to 500 milliamps, this motor. So I could set it to 500 milliamps to do some particular thing, and then just put it back down to 200 milliamps, all in G-code. So that would be quite nice. This is going to be my up-looking camera, and I've got a screen for that. So this is going to be it's quite a large one, but it's only 320 by 240, which is the native resolution for the picture that this is going to take, so it should look pretty good. The down-looking camera is going to be this Logitech webcam. I've butchered it a little bit, taken the case off, tried to make everything as light as possible. This is a Logitech B910. I think it's pretty much the same as a C920 that a lot of the streamers use these days, and it has autofocus, or has a physical, moving lens focus, and it has digital zoom. And I've modified the QV4L2, I think, Video for Linux, sort of a standard utility you can get for that. But I've added network connectivity, so I'll be able to connect to this over the network using a regular telnet connection, and I'll be able to set the focus and the zoom, on the fly. And this is for the closed loop steppers here. They're all running at 36 volts, and that's just a gigantic bunch of cabling for that. It's kind of funny, this is the only motor that doesn't need a long cable, because it's just going to go from here to here. These are probably going to be put about here,
or they're not going to move much. They're not stuck down yet, but they will be. Yeah, this is the only motor that needed a short cable, and it's the only one I had that had a massive big long one. These other ones I had to make up these extra cables here, and I wanted them to be light, so I'm trying some cables that are just USB cables. They came from an old webcam that I was going to throw away anyway, and they have 4 wires and a shield, so that's 5. You can get 5 wires in each one, which is kind of convenient because each one of these drivers here needs 4 wires for the stepper motor power itself, and then it needs 6 wires for the encoder, so that's 10. So with 2 of those I get 10 wires, and that's how this motor there is being run. And then I have another USB cable with just the 4 only to run the 4 motor wires for this little tiny motor. And I was a little bit worried because the wires inside those USB cables are typically very, very thin, because they're just, you know, for running the webcam, doesn't actually deliver much power. But for this motor I did want to deliver a little bit of power. But so far seems to be going okay. This here is just a 10mm aluminium extrusion tube, 1mm wall thickness. So it's probably not ideal. You probably want a steel one here, but I'm going to try this and hopefully it'll be alright. And it's not actually tightened down there. Oh, I can't turn it. But I found that just by tightening this belt, there's a decent amount of friction between the shaft and this pulley here, so it actually runs pretty well without having those grub screws tightened down. These grub screws are tightened down, of course, these two. Anyway, now I'm just really waffling, aren't I? I think I'll just finish it up here, and the next part we're going to have to do something about making these limit switches work, and also the next big task, I guess, is getting some sort of a vacuum system, relays and turn it off and on, and it's going to be really cool. So tune in next time when we do something with all the vacuum system. That's it for now. Thanks for watching.